Welcome to Lesson 2C, Volatile Liquids. We're going to talk about volatile liquids, especially how they evaporate in closed containers. What is a volatile liquid, or a VOC, which means a volatile organic compound? It's a liquid that readily evaporates at room temperatures. For example, gasoline, benzene, acetone, pretty much any VOC will evaporate a lot. Usually you smell it too, like nail polish or something like that, which is acetone. If you have a container of some liquid, like let's take water. I just have a water bottle here that's partially filled with water. If this has been sitting around for a number of days, what happens is the water here starts to evaporate until it saturates the air. Then it stops evaporating. So the air in this container is at the saturation pressure of that liquid. The same thing holds with any VOC, not just water. So this would be water vapor plus air. If you have a VOC, it would be the vapors of that VOC plus air in that gas. So in the water bottle, this is the liquid, and this would be PJ of the liquid, or the water in this case, would equal PV or PSat. And that always means at this particular temperature, because if the PSat varies with temperature, as we already know. So we can say that this air is saturated with water vapor if a long enough time has elapsed. So that's for water, but it applies to any VOC. We have exactly the same situation. So if I have a container of a VOC, so this is some liquid here, what will happen is it starts evaporating. Let's suppose the lid is put on. So it starts evaporating until the same thing happens. The air is saturated with, instead of water, it's just VOC, vapor, if a long enough time has elapsed. It's the same kind of idea. So for this case, we have in the air here, PJ is equal to PV or PSat, the saturation pressure or the vapor pressure at this particular temperature. So we'll talk about these kind of problems where we have VOCs in containers or in the air and stuff, and it starts evaporating. It'll evaporate until it reaches its saturation pressure, and then it'll stop evaporating because the air can't hold any more than that. And so that's how we know that that PJ is equal to PV if a long enough time has elapsed. So then the question is how to get PV for a given chemical. And what we will use is this NIOSH, online NIOSH pocket guide. And so take a chemical. So let's just use acetone as our example. And I'll show you this live. I'll go there and show you how to use this. So this NIOSH pocket guide, we look up the chemical and we can get all kind of properties like those listed here. So we go to the modules on Canvas and links and references, and then scroll down other websites. So these are my websites, and then other websites are ones that I copied from other places. So the online NIOSH pocket guide to chemical hazards is the second one on that list. And when you click there, it doesn't seem to work sometimes, but if you right click and then open a new tab, you'll get it to work. So let's do that. And now it's up here in that new tab in my Chrome. I'm using Chrome. Anyway, you can look at all the chemicals that start with J, for example, but I picked acetone, which is already an A. So you can hunt for it, or you can do a Control F and find acetone, and then you see all these properties. So there's the chemical formula, and there's its NIOSH REL and OSHA PEL. I'm going to talk about those a little bit. We also have some conversions and things, and then you have molecular weight, you have boiling point, you have freezing point, etc., vapor pressure. So this is the one we're interested in this particular lesson, is the vapor pressure for this chemical acetone is 180 millimeters of mercury. Watch your units as always. So back on our page here, the molecular weight for here, boiling point, 133 degrees F. Notice there's a mixture of English and metric units, which is always a problem, but be careful with your units. PV or PSat, the vapor pressure is 180 millimeters of mercury. When you need to convert, they're at standard atmospheric pressure. This is on the equation sheet. 101.325 kPa is 760 millimeters of mercury. So this turns out to be 24.0 kPa. Now, there's a NIOSH REL and a OSHA PEL. So NIOSH means the National Institute of Occupational Safety and Health, and they publish this recommended exposure level. Recommended's kind of a funny name. It's not like you're supposed to be exposed to this like recommended vitamins. This is what they call their maximum level, in other words, the upper exposure level for a particular chemical. And NIOSH is based on a 10-hour day for workers that are exposed to this. We're not going to use that one hardly at all. I'm just mentioning it because it's on the pocket guide, but this is the one that we're going to use for all our problems. Permissible exposure level, PEL. Again, it's the same thing. It's an upper limit that OSHA is the Occupational Safety and Health Administration. OSHA has authority to charge fines, and they can come and inspect your company and sample the air. So this is the upper limit for an 8-hour day and a 40-hour week. So OSHA has determined that the PEL, a permissible exposure level for a worker, a healthy worker in some job where he or she is exposed to chemicals, at that PEL, and for this particular case, acetone, the PEL is 1,000 ppm. So OSHA has determined that if typical worker is working 40 hours a week, 8 hours a day, 5 days a week for this company, and the air has acetone vapors in it at a level of 1,000 ppm, that's considered safe. And anything above that is considered a violation, and you can actually get fined if the company doesn't do anything about it. So that's my introduction to these VOCs, and now I want to do an example problem, partial pressure of a volatile liquid. So we have a half full can of liquid benzene. So benzene is our chemical, sits for several days at 20 degrees C and at atmospheric pressure, and I give the temperature and the pressure here as standard atmospheric pressure and 20 degrees C. By the way, these values on the NIOSH pocket guide are at 20 degrees C, not 25. So you'd have to look at other places if you want it more accurate than that. So I looked those up for you. So we have the molecular weight of benzene and the vapor pressure of benzene, and the equations that are appropriate here are given. And I want to calculate the mass fraction of benzene in the air in the can as a percentage. Okay, so let's set this up. We have this can, and here's the lid that's put on there and sealed tightly. Here's the benzene that's half full. So this is the liquid. And then again, as we discussed, the liquid will evaporate until you saturate. And when you see a word like sitting for several days, you know that it's had enough time to saturate. The pressure outside here is atmospheric, and we're going to talk about the pressure inside is not necessarily atmospheric. So we know that it evaporates until it's saturated. The benzene evaporates until PJ is equal to the vapor pressure, or 75 millimeters of mercury. Now I can calculate the mole fraction, Yj, equal PJ over P. And what is the pressure? Well, if we assume that the pressure is atmospheric pressure, and that's not necessarily true, but this would be 75 millimeters of mercury over standard atmospheric pressure is 760 millimeters of mercury. So this gives us 0.098684 as my Yj. And then the mass fraction comes from this equation. And we're going to actually need this later, but if we stay in variables, we would have Fj equal Yj times Mj over Mt, and then use this. This is equal to Pj over P, Mj over M total. And that's our final equation for Fj, the mass fraction, in terms of the given variable. That's our answer in variables. But there's several things we need to worry about. One is the pressure, and one is the molecular weight of the bulk mixture. So remember, this Mt is the bulk molecular weight, and there's a couple ways we can deal with this. I'm actually going to do 3 different methods here. So what is this bulk molecular weight? Well, method A is that we approximate that P in the tank is P atmospheric. That's not necessarily true, because as this liquid evaporates, it starts building up pressure inside the tank. Sometimes when you open a can that's been sitting around, it'll hiss when you open it because air is being released, because there's a higher pressure in there. Shake up a bottle of soda and open it and you'll see what I mean. So the pressure builds up as there's more gas in there if it's tightly sealed. So that's an approximation. And we also approximate that Mt is M air. So we're assuming there's a negligible amount of benzene gas. Well, there's actually about 10% from up here, but let's assume here that it's negligible just as an approximation. So with those approximations, this is really a quick and dirty estimate, not a very good approximation, but we'll see what it gives us. So here's our equation that we had up here. That's our answer in variables. And I plug in the numbers and I get 26.6%. This is an approximation. Notice that I used the molecular weight, standard molecular weight of air as MT. I approximated that, and I approximated the pressure in the tank as 760, or standard atmospheric pressure. So that's one quick way to do it. Let's do it two other ways. So let's look at, I'll call it method B. And what we're going to do here is we're going to calculate MT, the bulk molecular weight, but we'll still assume P atmosphere stays constant. So bulk molecular weight, MT, recall from previous lectures, is sigma yj capital MJ. And so here we have MT equals, when we plug in our values, we're going to use the yj that I had calculated up here, and then I'm going to use the molecular weights that I know. So I plugged in that yj, mj. Now we know that y air is 1 minus yj because all those y's have to add up to 1. Go back to one of the very first lectures. And then the molecular weight of air. And so I get this answer for MT. And now it's a matter of plugging into this same equation, but instead of using 28.97, I'm going to use 33.818. So I get my new, better, this is an improved version of FJ. So I plugged in all the numbers here for you, and I used this value of molecular weight, bulk molecular weight up here for MT. You can see that I still have the same MJ as I had before. These are all the same, and I get a new number, 22.8%, which is still an approximation. It's much different from here, 26.6, because we neglected the effect of this chemical on the bulk molecular weight. But this is a better approximation than we had before, so I'll say it's better, but we still haven't taken into account this pressure. So is that atmospheric pressure? Well, let's do method C, where I calculate MT like I did in method B, and I calculate the actual P in the tank, the actual pressure in the tank. So if it's perfectly sealed, and we put the lid on, we pour this chemical in, as I drew here, we pour it in, and there's just air up here, we put the lid on, and then we sit and wait. Well, what's going to happen? The benzene is going to start evaporating, and it adds some vapors into this air, so the pressure has to go up because you're not removing any air, you're just adding vapor to it, and the liquid level drops very little because it's a liquid, so it's very dense. So we ignore that, we're just adding vapor into the air. So the pressure has to go up. So how do we deal with that? Well, we recall, hopefully you recall, Dalton's law, additive pressures. So the P, or P total, equal sigma of all the species, sigma P of all the species. So here we have that the pressure, the total pressure, is P air, I'll do this in millimeters of mercury, 760, plus P vapor of the benzene. So we're assuming we waited enough time for all that benzene to evaporate as much as it's going to do. There's still liquid in there, and the partial pressure of the benzene is the vapor pressure. And so we get 835 millimeters of mercury. So now we just plug into this equation again, but remember the yj has also changed because yj is equal to pj over p, and so that doesn't affect that equation. But when we calculate mt, we had a yj in there up here, so we have to recalculate that yj. What I'm saying is that yj changes too, so our new yj is pj over p. So when we plug in this new pressure here, we get our new yj, which is different than the one we had before. In fact, it's smaller because we put a bigger pressure on the bottom here. Now we have to recalculate also the total or bulk molecular weight. And so that will become now y of the benzene times m of the benzene plus y of the air times m of the air. And without actually plugging in the numbers, I just want to point out that we have yj of the benzene, and then we have 1 minus yj of the air, since the y's have to add up to 1. And so I get for my new molecular weight 33.383, which is also different from what we had before, was 33.818. And then finally, we use the same equation that we had up here with the new values. So after plugging in all these numbers, I didn't put any units this time, and we know they all work out. You can actually see they all cancel out, pressure over pressure, molecular weight over molecular weight. And my final result then is 21.0%. This is the most accurate. I do have a couple final comments though. The first comment is if the lid is not completely sealed. So in other words, if there's a little bit of leaking going on, so air and vapors escape, and then this, if it does it very slowly, P is equal to P atmosphere. It doesn't gain pressure inside the tank. It just stays at P atmosphere, and some of the air and some of the vapors escape. And so in that case, method B is correct, or the most accurate of these methods. However, if the lid is completely sealed, so there's no leaks, then that pressure will rise inside there, and then method C, the last one, is most accurate. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.